Well, welcome to today's ICEA OEM. This is Bob Hunt, the current president of ICEA. I think we have a great lineup today, and with that, I'll turn it over to Karen Marikas. Karen?
Okay, good morning and good afternoon, everyone, depending on where you are. This is our agenda today. We're going to talk a little bit about digital engineering, give you some terms and definitions to help level set the discussion here. And that's because everybody has a different idea of what the terms mean. Well, not everybody, but depending on your particular company or your organization, you may define these terms differently. And so we wanted to share some of the terms that we've come up with across the company, or sorry, across the industry. And then we'll move into a presentation by Brian Beyer, who's from Boeing, and he's specifically talking about the T-7A Red Hawk Advanced Pilot Training Program and the digital engineering impact and, related to affordability. So moving to the next slide. Just a quick overview again of who we are. So the OEM COG, if you don't know what that means, the first bullet there says it. It's the Original Equipment Manufacturers Cooperative Opportunities Group. It's a mouthful, but basically we are a group of OEM participants who are affiliated with ICEA. So we have some interest in cost engineering, cost analysis. We might be from finance, from supply chain engineering. And we have representatives from different companies. And right now, the OEMs that have been represented are included there on that list. We've got BAE Systems, Ball Aerospace, Boeing, Huntington Ingalls Industries, Lockheed Martin, Northrop Grumman, and Raytheon. And this is open to other companies, especially if you're an OEM. So if you are interested, just reach out to us. And primarily our mission is to create a dialogue about things that are of interest to OEM members and ICEA members. So again, that has to do with the cost analysis, affordability, but specifically for the OEM community. All right, next. And today we're going to talk about digital engineering. I wanted to share this slide because I thought it was a good representation of a bunch of the different terms that you're going to hear today and kind of how they're all related. I do want to give credit to, it's the US Air Force Digital Enterprise. They had the Global Product Data Interoperability Summit, or GPDIS, in 2018, and Colonel Paul Harmer and Dr. Paul Hartman put together this presentation, or a presentation, and I found this slide in it, so I wanted to give credit to them. But primarily, the takeaway from this slide is that you can see the scope of the different terms. You can also see that they overlap. Now, looking at this, you may say, well, that's not how I would define it, and that's perfectly fine, because that's the whole point of the OEM COG. We want to look at things from different perspectives and just get a better understanding. So just very quickly, the definitions we're going to cover are digital engineering, which is the light blue. And then we move down to, we've got MBSE, we've got digital thread, MBE, and digital twin. So just very briefly, we're going to give you an overview of those, and then we'll go into our presentation. And so for our first definition, we can go to the next slide. I'm going to turn it over to Vicki Moeller, who is from Ball Aerospace. Oh, and one last thing that I want to say is that, again, these definitions come from various sources. You'll see down at the bottom, we've got public sources, professional organizations, the DoD, and from some of our own companies. But the person who is speaking is not necessarily sharing what's coming from their company. This is just an overview of several of the definitions that we found that we wanted to share. So take it away, Vicki.
All righty, thank you. So good morning / good afternoon, everyone. Digital engineering, especially from a terminology perspective, is a really interesting thing, and it will not do your dishes, but there are a lot of things that it can bring in terms of benefits for companies and benefits for industry. So a lot of what we're seeing here, especially as you look across these definitions, you're going to see the words integrated. You're seeing authoritative sources. A lot of times we'll have data that we're accessing as a program that will be on a file server, and it is static data that is not necessarily tied to anything. One of the big goals here of digital engineering is to start pulling those pieces of data together to actually integrate them so that there are single pieces of data rather than 4 instances of the same piece of data. Another thing that you're seeing here is we're pulling in computer models to do a lot of that integration. A big piece of this as well is that digital engineering goes across disciplines. And specifically here, especially for this group, it is not just engineering that is affected by digital engineering. It is something that affects finance, IT, mission assurance. It's really a very broad spectrum term. So with that, I think we'll jump into John and let him talk about from Lockheed and talk about MBE, model-based engineering.
Okay, thank you, Vicki. I think the first sentence really defines model-based engineering pretty well. Treats models as an integral part of the technical baseline as opposed to documents. So under digital engineering approach, like Vicki just described on the last slide, a digital technical baseline is really a key enabler to digital engineering, where the digital models, the virtual representations of the physical designs are the technical baseline, rather than in a traditional approach to engineering where the technical baseline was just a collection of documents. So MBE, or model-based engineering, is essentially a digital technical baseline. And as in the traditional engineering environment, systems engineering really drives that technical baseline, at least my perspective. And that just, in this case, the technical baseline just happens to be digital. So that's kind of the essence of it. And from here, I'll go back to Vicki to address model-based systems engineering.
Alrighty, thanks, John. So going into model-based systems engineering, the big key of this is that it is not document-based. So like John mentioned, we're focusing on models in order to accomplish our systems engineering. And those models are of architectures, functions, requirements, interfaces. They're those big things that you think of when you think of systems engineering that the systems engineers typically take care of over the course of a project. Those are captured via either a single model or an integrated series of models. So a lot of what you're seeing here, again, we're finding a lot of common terminology across the definitions from various companies, even from various industries. A lot of what MBSE allows us to do is to find those problems early. It allows us to do V&V early in the stages of the design. For those not familiar with the term, V&V is verification and validation. That's basically proving both that we built the right thing and that the thing is built correctly. And those models can help us do that digitally before we ever get to hardware. So that in itself is a major cost opportunity that we find. And so I really appreciate looking at all of these definitions and seeing a lot of the commonality there. Again, one of the big things with MBSE is that it does go all across the design lifecycle, and that we're starting from concept and able to communicate with our customers and our subcontractors from, hey, I have an idea, all the way through, okay, our product is done, it's at the end of life, and we can now close out our model. So MBSE is definitely a powerful tool, and I will pass it back to Karen, and she can talk about the digital twin from Boeing.
Yep, so actually I'm talking about the digital thread. And one thing I wanted to point out is up in the upper right-hand corner, you see that graphic that we shared earlier. So the digital thread, if I can see, it's pretty small. I think it's the blue, the dark blue one in there. You may or may not agree with that, the graphic representation, and that's okay, because again, that's part of this whole, the purpose of this group. So digital thread, we're really talking about the communication and the data flow from one piece to another piece, from one function to another piece, another function, all the way through the entire life cycle. So you can think of it as, initially, we may have had the documents that both John and Vicki talked about, and there may be different versions of those documents. Okay, now in this model-based environment, we can have a digital documents, I'll use that term, where everybody has access to the same piece of information. There's no configuration control issues. There's no, hey, my version of this document that's stored on my computer is a month old and it's been changed since then. So really it's all about making sure that we've got the connection to the data, to all the analyses that we're doing, and that connection will exist all the way throughout the life cycle. And that very last line is talking about from concept through design, manufacturing, and service. And actually right before that, in the middle, it says it's an unbroken link from the original computer model to the final physical product. So I really like that definition. That kind of resonates with me. And finally, we will go to Sandy Burney, who is from Northrop Grumman, and he will talk about digital twin.
Thank you, Karen. So the digital twin is really a high fidelity model of whatever you're trying to, your ultimate product you're trying to build. And it turns out, yesterday I happened to see a briefing of an actual digital twin for a product that my company is building. And as a cost guy, it was actually kind of interesting because the cost savings is that they can do this representation of this board and software, and it was being pushed by the tester so they could start testing early, so to stop rework. So because they were building a board and software and representing this, in real time, the interesting part is that they needed essentially a supercomputer to run this digital twin. So the interesting part, so there's cost savings, but there's also a very large upfront cost for the infrastructure to be able to do digital twins and to maintain it. So that was kind of the interesting part of this briefing. So I will now pass it back to Karen to introduce our guest speaker.
All right, so we are going to hear from Brian Beyer, who is from the Boeing Company. He's in the technical fellowship at the Boeing Company. Again, he's going to be talking about the T-7A Red Hawk Advanced Pilot Training Program. And just a little bit about Brian. He's been at Boeing for, I don't know, I'm going to say maybe about 20 years or so. And he's worked on various programs, most of them defense programs, in a variety of roles. I first met Brian about maybe 8 years ago or so when we were both working on this program, although at the time it was called TX because it wasn't a program. It hadn't been awarded at that point. And Brian was the affordability lead for that program. And what he did was brought a lot of different perspectives together. So he had team meetings where he's bringing in finance, supply chain, engineering, the various engineering disciplines, and all talking about cost and affordability. And I think sometimes when people hear the term affordability, they automatically just think, oh, this is cost. But Brian did a really good job of bringing in all these other perspectives, which is really the way you need to think about affordability. Anyway, with that, I will turn it over to Brian Beyer to talk about the T-7A Red Hawk Advanced Pilot Training Program.
All right, thank you, Karen. Hopefully you can see my screen okay.
Yes.
Thank you for the introduction. I appreciate that, Karen. Yeah, I'll very excited. Thank you for the opportunity today to talk about the T-7A as far as digital engineering and the affordability benefits thereof. Definitely honored to speak today. So I'll just give a quick little background about myself, and then I'll dive into some of the information about the program and the information and some more background about digital engineering and what we're doing there. Let's see here, next chart. All right, there. Can you see my chart on about my background?
Yes, it did advance.
Thank you, Karen. All right, perfect. So just a little background about myself, and actually had a metallurgical engineer by degree with a master's in systems engineering, and had actually spent, as Karen mentioned, 20 years, but had spent a little bit of time actually in steel making, believe it or not, and then in high temperature alloys, a little bit of time in jet engine overhaul at Pratt & Whitney United Technologies, which is now Raytheon Technologies, before I came to Boeing. And then I've been privileged to work a number of programs across Boeing, from our fighters and bombers to our advanced trainers to some of our training systems in our Boeing Global Services division, as well as unmanned systems. I've also worked on some of our programs over in weapons, some of our weapons, direct attack weapons and such. So it's been quite exciting. Been able to spend quite a bit of time working across functions as well, which I think is really important to an affordability leader. To have a broad view, and in system engineering to have more of that integration view, right? And so you've got the breadth and depth across systems engineering, across product, across production system, across the life cycle, if you will, of how our products are utilized. I'm also certified in Six Sigma, or Six Sigma Black Belt. I've spent quite a bit of time with our lean groups and lean design, lean manufacturing, and some other areas in value stream mapping, some of that sort of thing. So I think that's been really beneficial to my background as a continuous improvement, process improvement, product improvement type person, or focal. For today's agenda, we're going to go into, so I'm going to talk a little bit about just kind of industry, current state of digital engineering and what I'm hearing out there in industry, what you are likely hearing out there in industry from our customers. As well as other folks out in aerospace and beyond aerospace, in automotive and some of the other areas. Talk a little bit about digital, obviously quite a bit about digital engineering at Boeing and what we are doing, as well as the T-7A program. I'll give you some more background about the T-7A program itself and what we're doing there, and then model-based benefits or value of model-based engineering and digital engineering across the life cycle. If you look at the development phase, the production phase, and sustainment phase as well. So, but it really is a journey, and that's the other point I'll make through this way. It's something that's evolving over time. I don't think there's a true, nirvana, if you will, or ultimate state of digital engineering. It keeps progressing, right? We all keep progressing and moving forward. So it's really like moving along a roadmap. The way I'd look at it. Some of the things that I'm seeing in industry, and if you go out and do some research on the web, you're going to find a lot of different information on digital engineering. Again, from other companies, other industries, from experts in different societies. This just talks about some of the things that I've in recent research in the last year or so pulled together. There was a lot of information, as you know, from Will Roper and the Secretary of the Air Force in his previous role, utilizing the matrix as a kind of an interesting use case, right, to talk about, digital and virtual reality. When you look at that, you've got a number of papers, if you will, 2 or 3 different papers and such that have evolved into the digital guidebook for engineering in the E-Series designation. I wasn't going to go into that as much, other than it provides a lot of good background of where the customer, at least where the Air Force was working or where they were trying to go with digital engineering. Since Dr. Roper's left that position, and Frank Kendall's come into his role as the Secretary of Defense, I think they've changed the moniker there a little bit. They've changed the emphasis on the E-Series. They've kind of reduced the emphasis on E-Series. Originally, that was one of the questions that was asked of me is, hey, could you explain what does E-Series mean? What is that all about? And it was announced last September of 2020, that the TX was the first E-Series program, right? All digital, and you can see some of the words on here, that some of the folks in the Air Force had given us credit for, as far as virtually designed, built. We ran through hundreds, if not thousands, of simulations and optimization runs, leveraging that all digital modeling, high fidelity digital modeling, and that's kind of one of the reasons why the TX program or T-7A was getting recognized as an all digital E-Series program. So I mean, there was like the Department of the Air Force, right, letter memorandum that came out in May also about this as well. If you're looking for some good background information, I think some of that's been, again, kind of de-emphasized by the current administration for various reasons. So I won't go into details there, but again, a lot of good background information about the intent for working to achieve E-Series and what the kind of goals and criteria were. You can also find some good information out there at Air Force Works, at some of the information about what's going on in disruptive innovation, also acquisition, digital acquisition. There's some really good links here. I just wanted to share some of this in my research and background that could be helpful to you out there as you're looking to learn more about the topic of digital engineering, model-based engineering, and where our customers, at least the aerospace, defense customers, are wanting to go with this capability technology. So we'll move on. All right, as far as T-7A digital engineering, I appreciate the intro. I think this is great, and all the definitions we discussed today from an industry perspective about what is digital engineering, model-based engineering. I'm going to just briefly talk a little bit more about that from a T-7A or from a Boeing perspective, about the way that we've instantiated that or evolved the discussion on that. I mean, we read the definitions there. It's an approach that takes traditional engineering processes, right? We think of document-based engineering and kind of simplistically used to develop, fabricate, build, test, right? We've all evolved or used models for various purposes and reasons, for aircraft development, right? Or doing strength and stress, or aerodynamics modeling, and capture those in high fidelity models. That's evolved for 30, 40 years. But I think what's important is more integration of all those digital models, those high fidelity models, in a more collaborative environment. In this case, it leverages a single source of truth, design data. We talk about the interconnectedness of those models, which is really important. And it's not just the architecture. A lot of our teams, or some of our teams, think of just the MBSE as architecture. Like you might document the architecture, the blueprint of your system in Cameo, for example, which is one of the main modeling tools we use, no magic Cameo. But it really goes beyond that. It's really the analysis, the optimization, the simulation, and being able to optimize a system digitally or virtually before you actually go out and build the real thing, right? So you can do a lot of risk reduction. You can do requirements validation, verification via modeling, high fidelity modeling. So if you look at the right here, the bottom, I just put reference to this. This is also a link to the GIPDIS, or the Global Product Interoperability Summit, where Dan Seal and some of our folks from Boeing had presented, the Boeing Systems Engineering Diamond, as we call it. So if you look at the classic Systems Engineering V that most of our engineers and system engineers are very familiar with, which is kind of represented on the lower side here of the diamond, that's your classic system engineering, taking your needs, your CDD, your capability description document, right, your mission needs, and right, documenting those and allocating, deriving those down through your system, from your system level down to your subsystems, typically into your components, right, that kind of work. And then building up usually a physical system. It can be a prototype, could be your initial product, and then working the verification, validation, certification, and eventually delivery and operations and support of that particular product or vehicle, that if you will. What this represents here on the diamond is also the creation of the digital models, or the high fidelity models. At the same time we're designing the product or production system, even we want to create a high fidelity digital twin, right, or a digital model of that. And then the center here represents the digital threads, across the life cycle and across these different disciplines and the different phases, if you will, that utilize that single source of truth, if you will, for the different disciplines to do their analysis as we're trying to work through that system engineering V, if you will. So I think we realized that we were in need of an update. This was really driven from the highest levels of our engineering community from, Greg Heislip and Todd Citron, our executive or senior level engineering leaders down through the organization, that we needed something more modern that really represents what we're really doing with digital engineering, digital thread. So I think this was a good way to really capture that and show that. And I could do a whole presentation, or we Boeing system engineers could do presentations just on this, for an hour. But that's out there. There's some information and videos out there on the web that have been released through some technical webinars more about this. So you're welcome to follow this link or find that out there. But obviously the benefits of doing so are really increasing collaboration among the many different stakeholders, as well as the different disciplines. And again, that's from a model-based engineering standpoint, is really beyond just systems engineers or engineering. It's across the other users of the other teams that are helping develop, build, test, support, and eventually sustain that particular product or system. So those integrated models make it much easier to share and reuse that design data, the analysis data, the optimization, right, and do more efficient and effective verification. A lot of your traditional V&V verification validation work that was done during test or actual physical testing of a system can now be done by, actual high fidelity modeling and analysis. So quite a bit of that work can be done by analysis, and as our models become more connected, and we can validate the fidelity of those models and the accuracy and integrity of those models, then you can actually get more efficiency out of utilizing them for V&V. And it also reduces errors, right, or produces better first-time engineering quality. So having a single source of truth, having all of your engineering disciplines work off of that single baseline or truth data provides a lot of value. So let me move on down the line here. So transitioning from digital engineering and the diamond, how do we apply that across the different phases and the different products that we were developing as part of this advanced pilot training system? So if you look at the system itself, it actually, so everybody thinks of the aircraft, right? The aircraft is, the training system, but it's really not. It's really just the final validation vehicle for the pilot that he's ready to, enter into another Air Force jet. So just like replacing the T-38C, but with a much more modern, more advanced training system, so that they're ready. Our pilots are ready for 5th-gen aircraft training, or actually flying their, F-35, F-22s, but also use it for training other air vehicle. It can represent, if you will, the cockpit is adaptable to represent, F-18's cockpit, F-15, A-10, a multitude of aircraft that the Air Force uses. So it truly is a multi-purpose, adaptable, flexible training system. So besides the aircraft here, and I'll talk about some of the features of the aircraft in a second, you've got the purpose-built ground-based training system, or what we call GBTS. So this includes a number of different devices, from desktop devices, very simple, you think of your kind of simulator, desktop simulator type device, all the way up through what we call the Operational Flight Trainer, OFT, very high fidelity training devices. I've got another chart on that, what that looks like. So that team or group leverage model-based engineering as well. And I'll talk a little bit more about the connectedness of that here in a sec. Also the purpose-built support and sustainment system as well. So design for supportability was also very important, or a design parameter that we leveraged beyond just design for affordability, design for manufacturing assembly, which I'll talk about in a minute as well. Design for supportability, so developing that support system, sustainment, maintenance, integrated logistics, integrated vehicle health management. Those were all part of leveraging model-based sustainment, as we call it, or design for supportability early in the product development phase, back when we were working on the TX PRJ, what we call production relevant jet phase. So all these were part of that digital thread, if you will, or part of that development program. So I'm going to take just a moment here to pause. I'm going to play a video. Was there any other thing coming in, or any things coming in the chat that I need to be aware of from our panelists?
We haven't gotten any questions in the chat or any chats, but folks on the line, don't be afraid. Send your questions in the chat box, and we'll get to them when we can.
By all means, thank you. So I will pull up there, and I'm going to turn up the sound here a little bit here, see if we can get this video to work for you. But just this is going to show you a little bit more about the digitally connected benefits or features of the aircraft. It's going to show you a little bit more about the airplane, talk a little bit about the training system and some of the design philosophies. It's a short video, and hopefully this will come through here. Turn this up.
Deliberately designed and now leaning into the second phase of flight testing, one of 2 Boeing purpose-built jets for the U.S. Air Force T-7A Red Hawk Advanced Trainer Program taxis into position. All right, we're ready to take off. And Chief Test Pilot Steve Schmidt pushes the throttle forward. Nozzle's good. Just coming up. The future of U.S. Air Force advanced pilot training is aloft.
I'm Paul Newald. I'm the Vice President and Program Manager for the T-7 program here at Boeing.
Okay, flight control check.
This is an exciting day. This is where we go demonstrate high angle of attack maneuverability as well as departure resistance.
Key elements in demonstrating the fighter-like performance of the agile jet went from model-based engineering and design on a laptop to first flight in just 36 months.
Digital engineering has really been a game changer to this program. We're actually flying at the same time we're building the new jets.
In fact, it's because of the T-7A's digital DNA that an anomaly at higher angles of attack called wing rot was discovered long before the first U.S. Air Force pilots ever climb into the cockpit.
It allowed us to identify issues early, get those fixes in. We probably wouldn't have discovered something like this until 2 years from now.
Those fixes were loaded into the jet's updated operational flight software and are being validated today.
Record 53, climbing in level 350.
My name is Brad Nelson. I am the Senior Test Program Manager for the T-7A program.
Wind up targeting 5 Gs.
We've been able to move through our testing much quicker than we have on previous airplanes because of that digital engineering.
Even so, the COVID-19 pandemic has challenged the program and its global supply chain.
We're seeing the impacts of the pandemic in our build, and it's delayed parts coming to us and thereby delaying us putting the aircraft together.
Newald says that the team is committed to making up any delay in schedule by using the same innovative mindset that's fueled the T-7A Red Hawk program since its start. And no one knows that better than the pilots who are flying the advanced trainer into its second phase of testing.
It flew squawk free, so we were extremely happy with the way the jet performed.
It's what I love about this team. They don't take anything as an excuse, but as a challenge to make sure that we can deliver this system to our Air Force customer to give them the best training system ever.
Center 13.35.
Let's see here. I'll make sure this. Here in a minute. All right. Hopefully that came across okay. I'm going to go back to the presentation here. All right. Our panelists, is everybody still on board? You guys can hear that okay?
Yeah, that came through fine.
Okay, perfect. All right, thank you. So yeah, just to give you a little idea of digital engineering and a little overview of the aircraft itself, what it can do. You heard about some issues that were popping up as you would expected, or you would expect in the engineering and manufacturing development phase or program. Those things happen, and we're addressing that. We're utilizing what Paul was talking about there, was leveraging or utilizing high fidelity models to work through those issues earlier than we would have normally. Actually found those in flight testing. They actually predicted that we would have some potential instability or wing rock issues up above the 25 degree or around the 25 degree angle of attack due to the high fidelity models that were leveraged, and that we had captured that data through wind tunnel testing and validated that relative to the TXs or T-7As airframe design. So actually that's kind of what he was getting at there, is that we were able to leverage modeling to predict that, see that, address it, and start working through the root cause of those issues sooner. And then we're able to use software, in this case, through the the flight control system software to basically fix that issue, what they were calling the wing rocker stability issue. So hopefully that gave you a little bit better look at why and how we can use digital engineering to, not just be more efficient, but solve problems as well and help us from a first-time quality perspective. Also here, I'm just gonna show the aircraft and some benefits here. We did a lot of work up front on design for affordability, looking at benchmarking best practices across other programs back in the 2012 timeframe when we were just kicking off the PRJ or production relevant jet phase of TX. So at that time it was very much an early concept, and so coming up with an affordability strategy aligned to, with the Air Force's vision and goals for what they needed out of a future, next gen trainer in a training system that was going to be much more advanced, digitally advanced, and provide the right capability for training fifth generation sort of fighter pilots. So all that basically got rolled into our design for affordability strategy. And so it was very much an intentional, proactive design for affordability or affordability program that we had kicked off or initiated right away at the beginning of the development phase of this program. Let's see, I was going to just mention, model-based design. Teams I'm sure our engineering teams, they've been utilizing our design engineers, structures engineers, subsystems teams have all been leveraging model-based engineering for 30 plus years now. So that's not really anything new. I think it's just evolved as far as the fidelity, integrity of those model-based design or MBD models. And then also being able to review those models in more efficient ways using tools such as like VisMockup, which is really like a kind of a way to visualize or see those models, turn on and off layers of those models. I think, again, our design teams are very mature in that area. I think where we've seen a lot of value more recently is documenting the architectures, again, the analysis and some of the other optimization work that we're doing in conjunction with, the physical, what we get, engineers always think of the physical design aspects. We're also talking about the logical, the behavioral, right, and some of the other aspects of the design as well. Let's see, the other thing I want to mention is, as we were working trade studies, right? Trade studies, a lot of, alternatives, considering alternatives from the air vehicle, from the configuration level, all the way down through the subsystems into the components that we were choosing, cost modeling, if you will, or our high fidelity modeling, parametric modeling was also critical to that as well. Working together, creating an affordability working group that was multifunctional, that was folks from our engineering teams, operations teams, supply chain, as well as finance teams all working together was really critical to, designing this air vehicle for cost, if you will, or for affordable, say value, if you will, the most value. Let's see. So that was a little bit about the air vehicle or, the product design itself. And some of the features, the affordable features of that. I also want to mention that I think it's really important that, and there's been several news articles recently on Defense Daily and Aviation Week about, the build process as well as the production system. So you'll see that these pictures actually were pulled from a couple of recent articles out there. So what was also important for us and what was really valuable was actually developing the production system design or designing the production system at the same time we were designing the air vehicle. So, versus it being an afterthought, leveraging our, production system teams, our production system best practices, our production system design and analysis processes up front, early in the design phase to generate and create requirements for the aircraft to make it more producible, right, to design it for manufacturing and assembly. Again, from an engineering side, that's nothing new, but I think it's how we leverage the digital modeling to do that more efficiently and effectively. So we can actually run simulations, right, optimize the production system sooner, earlier than we traditionally have. So what you're seeing here on the left is the forward fuselage assembly, which there's been a number of articles out there, which I reference here again about precision assembly, full-size determinate assembly or determinate assembly methods leveraged or utilized for the aircraft, which we've deployed across the entire air vehicle. On the right-hand side, you see the aft fuselage assembly in Linköping, Sweden, as that's built by Saab, at least for the EMD program. You're going to see I think there was actually just an article out in the last day or so about Saab opening their facility or getting ready to open their facility in West Lafayette, Indiana, right near Purdue University, which they will be building from LRIP or low rate initial production forward through the whole full rate production program. They'll be building this full aft assembly in the United States. So that's a big deal for our partnership and for them to have that assembly here in the US. It'll definitely help out with collaboration. But one thing that was really critical from the design phase, Saab's got full ownership of the aft fuselage design. So leveraging digital models, of course, working to that single source of truth really helped the teams collaborate across the Atlantic, across the ocean when we were back in the development phase. And of course, it's still critical for us to work together in that partnership efficiently and effectively. So again, another good use of digital models to share data and design data and other types of data with our suppliers, key supplier partners. And then, so speaking about the aircraft and the production system and leveraging the production system design and model-based engineering for that, also the advanced pilot training system. So this is a whole series of products or deliverables that are part of the contract line items or CLINs for the APT program, as well as the aircraft. So you've got, the part task trainers, you've got your ground egress trainer, you've got, ejection seat trainers, which are mock-ups or models of the ejection seat, unit training devices. So there's some lower fidelity, but higher fidelity than part task trainers. Where they're going to really learn about the instrumentation of the aircraft, the avionics. You've got the operational flight trainer, which they're going to get in and do full, very high fidelity training and really get ready for the, flying the actual aircraft itself. They can also do a lot of testing in here. We did a lot of testing during the development phase of the OFP, the Operational Flight Profile program, the software basically for the aircraft, and did a lot of testing in our integration labs, right? So that's the other benefit, right, of digital model-based engineering, is being able to have our flight simulation team, our aircraft development team, as well as our training systems development team all working together. Physically, they can be, but also working together with the same data models, software, the same integration labs. That was really valuable for the team to create a better overall integrated pilot training system versus just the air vehicle itself. So all these are really critical to the program itself. There's a number of devices. I think it's 40 something devices initially on contract to be delivered to the Air Force to do the pilot training, and then the mission debrief piece of it as well. But there's a number of areas that all leverage model-based engineering, digital engineering, the digital twin of the physical assets, the digital twin being the modeled version of each of these training system assets that we'll be delivering. And then you've got the purpose-built design for supportability aspects of the aircraft here as well. So, built with maintainers in mind. So obviously this is very important to getting a lower cost per flight hour, cost per tail of your air vehicle, so that the Air Force can afford to operate it, maintain it more efficiently with a lower budget. Right? They want this thing mission capable, and they want it flying a high percentage of the time. Obviously, they don't want it down for maintenance. So designing it to be more reliable. Designing it, for minimum mean time to repair, or so repair times are really quick and efficient and easy. Designing the physical aspects of accessing the equipment, up front in the design, creating requirements for design for supportability was really critical. And then of course, leveraging model-based engineering and virtual reality reviews with those supportability and maintainers, design for supportability engineers, maintainers. So getting your LEDs, if you will, your system engineering experts in developing those models early in the development phase, again, helped us create a more optimized solution for the operators and maintainers as well. Let's see, I just was going to share another quick video here. I think it was actually queued up and ready to go. So let's do that.
Set to prove out the Boeing T-7A in inverted flight, Boeing test and evaluation pilots Matt Geesey and William Berryman are the first to take the advanced trainer developed for the U.S. Air Force through a rugged series of maneuvers, testing the jet's fuel system at all angles.
So what we do is we roll the airplane upside down, and we need to make sure that things like fuel, oil, everything else feeds properly to the airplane during this negative G testing.
Clear to maneuver, item 960.
Cutting through the skies over Missouri, the agile advanced trainer lines up for the first crucial test point as a chase plane follows.
Okay, Bravo's visual, we're starting to close. Tally ho.
On the ground, test engineers in the telemetry room monitor every system on the jet and give the crew the go-ahead to invert at high speed.
Data's ready, verify chase in position. Chase at position. So here we go. In 3, 2, 1, now.
Rolling the jet over the head-up display gives a pilot's eye view, icons spinning, as a cockpit camera captures the world turned upside down for the aircrew.
1, 2, 3.
We rolled to an inverted flight position and pushed to -1 G, so it's a little uncomfortable. You're kind of hanging in the straps in the seat.
10, 11.
You know, our task was to go fast and upside down.
It went perfectly as scripted. It was flawless.
Rolling up.
Historically speaking, airplanes need to demonstrate the capability to operate for some period of time in maximum afterburner at maximum fuel flows at -G. This airplane met those requirements with flying colors.
Throughout the series of a dozen separate inverted test points, some as long as 12 seconds, multiple aircrews prove the Saab-designed fuel system is efficient and reliable in the advanced trainer as it prepares for a light of future training missions and beyond.
It's a great trainer lead-in to the current fighter fleet, but at the same time, it could serve multiple roles as a light attack or otherwise fighter.
367, 1250 with 11.
All right. Close that out. All right, that was the second and final video I had to share today. So I think maybe the point may not have come across there in the video, but the use of high fidelity models or simulations and modeling for the fuel systems to make sure that they were going to operate properly, safely, efficiently. We weren't putting the pilots at risk. It's not like the pilots just get in and go out and do that as a kind of an initial verification test. You know, this has been done by analysis in high fidelity models prior to that, right? We want to give those pilots confidence that the airplane's going to function properly, and so that's again another point of utilizing and leveraging those digital models, and that's leveraging Saab's digital models and some of our other key supplier partners digital models and sharing that single source of truth so that we can provide our pilots confidence that the air vehicle is going to behave and act like it's intended to per its design. There was also a flight test similar to this with the production relevant jets that we went out and actually turned the engines off. So we actually flew and the pilots turned the engine off and just basically flew to prove out a restart, mid-air restart. So the engine's off for, I forget, it's like 30 seconds. It's basically just gliding along. I mean, pilots don't like to do that. They don't like to shut off the engine in the mid-air and just glide along there. But that was part of the final verification testing or validation of the system that they're going to work properly in an emergency to have to relight the engines and fire it up. But the reason the pilots had so much confidence is they'd done that in the simulator. The engineers had done that in the high fidelity models on the ground, right, and proven all this out and done it ahead of time. So it really was just a final, validation at that point. So I think that wraps up the key points of my presentation today. I am open for Q&A, and I'm just going to stand by here and let the panelists take back over and help answer any questions that I can.
Awesome, thanks, Brian. Our first question came in from Albert, and he asks, can you comment on any of the obstacles experienced during the transition to model-based solutions?
So from a Boeing or T-7A standpoint, it's evolving. Back in 2012, 2013, I mean, we were definitely less mature than we are now with model-based engineering. There was a number of challenges with some of the integrated product architecture processes and tools we were trying to roll out back in the 2014, 2015 timeframe for T7. So the program, this was a Boeing funded, it was an internally funded, IRAD and CFR, it was our own funds, NBF, New Business Funds program. And so, we had brought on some of the capability teams from our core system engineering group to help us deploy MBSE and model-based engineering in some of those kind of earlier days from an architecture standpoint. And back then working to, system level standards and even some of your DODAF views, trying to create the proper architecture for their vehicle. And there's a little bit of struggles, they're trying to get the teams up to speed with the latest capabilities of those tools, what tools were going to work for us and not, and how to kind of transition over from quote unquote document-based engineering to model-based engineering. So I think it was definitely a more transitional type process. We've evolved a lot since then, and 2021 we're much more advanced today from the standpoint. But again, I see our new development programs and PhantomWorks that I'm working on, and again, it's still evolving and developing.
Excellent, thank you. The second question we got comes from Ben. Is the software used to create the digital twin something purchased or something each company has to build from the ground up?
That's a good question. So I think, depending on what the digital twin is, so if you look at some of the like multidisciplinary analysis and optimization, MDAO, you've got companies out there like ANSYS, Phoenix Model Center that, are creating quite a bit of the, standard industry-wide models that we use that, Northrop uses, Lockheed uses, Raytheon, a lot of you out there online today use, and then you're probably custom tailoring it or utilizing it in your own sort of fashion, integrating other plugins, APIs, software interfaces to that sort of framework. So we leverage quite a bit of off-the-shelf software, if you will, or industry software, if you will, PLM software or Cameo type software, architecture software, and then we typically will do a lot of the integration kind of within Boeing or with our own teams.
All right. Third question is from Raymond. We're doing all right on time. What tools do you use for your high fidelity parametric cost modeling?
Good question. I mean, so, Excel is probably one of the most common ones, right, to use, but in reality, we end up using several other tools. We use the price true planning suite of tools, which offers a lot of capability for, top-down parametric cost modeling. We also leverage SEER, the Galarath SEER suite of tools. If you look across all of our different use cases for defense, for global services, for Boeing commercial airplanes, there's multitude of use cases from, bottoms up process-based modeling to top-down system and aircraft modeling, rotorcraft modeling, satellites, modeling, large BCA commercial airplanes. So there's quite a bunch of different product domains, and we leverage a multitude of tools to do that parametric cost modeling.
All right. Our next question starts off with a compliment. Really cool stuff. It's from Chris. I'm curious how closely the forecast mean repair data in the digital environment tracks to real world performance.
That is a good question. I don't know. So we built the two production relevant jets. They were intended to be obviously much more mature than just a prototype, and those are out flying, and we've been maintaining those in hundreds of flights. Test flights, but we're still working on the first couple EMD or engineering manufacturing development units and building those up. So those haven't actually flown yet for T7. So we don't have much data yet on any of the support and maintainability piece. So I think some of those models have been validated with other similar to systems where there was a lot of subsystem reuse from F-18ENF and F-15 and other programs. So that's how we've done a lot of the validation to date, but there's still work to go there to validate the actual T-7A systems on an operations standpoint.
Okay. Then from Greg, thanks for a very interesting presentation. Any thoughts on the overall rough percentage program savings when comparing to a pre-digital engineering approach? I would expect, of course, that each design and functional savings would be different for each phase through the life cycle.
Yep, that's a great question. I think we're all trying to figure that one out, what the benefits or savings are. We've taken a lot of those lessons learned in model-based engineering, digital engineering into our new programs and really tried to design for affordability and for value and first-time quality. And it's a moving baseline. That's the hard part, is when do you strike a baseline of what was the previous state? You know, for us, it might have been, you know, an F-18 ENF development. It could be, you know, a Phantom Works project that we did, you know, in more of a traditional document-based fashion. But model-based engineering has been evolving for 30, you know, I could easily say 30 plus years. So it's hard to nail it down. You really need to, you know, pick a starting point. Say, okay, this is our starting baseline, and we're going to compare all the benefits and the value of model-based engineering that's evolved since that point in time, and try to figure out the savings. But we have seen a number of savings in verification, validation, testing, flight testing, you know, all the lab testing, you know, through analysis models, high fidelity models, and leveraging those models for that within development. Of course, in production, you're seeing better quality. You're seeing parts fit together more accurately, more correctly, so better productivity, less touch labor, right? Less rework from that perspective. And then in ONS, specific to T-7A, we don't have a lot of operations sustainment data yet, but hopefully we're going to see better mean time between failure, higher reliability. We're going to see lower time to repair, more efficient operations, higher mission capability rates that we'll be able to quantify at some point in time.
Excellent, thanks. So then we've got a question from Stu. Was there a predicted reduction in the development schedule as a result of digital engineering, or did the program realize a reduction in the development timeline?
Yeah, that's a great question as well. Obviously, that's a big intent of defining requirements, having a single source of truth, having a model baseline that we can leverage early on in the development phase as you're working through your PDR, CDRs, so that you can build and test the air vehicle quicker. So you saw T-7As, the PRJs, the production relevant jets we talk about, the two air vehicles built in 36 months from pretty much early in design, pre-PDR, all the way through the first flight, 36 months. That was pretty aggressive. Again, it's not a fully integrated fighter with all the mission systems and complexity of new modern 5th generation fighters. So I totally get that, but it was a lot to do and accomplish in 36 months, and model-based engineering certainly helped accelerate that schedule.
Next one's from Jason. Where do you expect to see the greatest savings across the program lifecycle?
Another great question. Yeah, I mean, we're expecting to see savings, in the development phase later on. Well, you're actually seeing, first-time quality benefits, right away from, digital engineering, model-based engineering, just because all the different disciplines in engineering can leverage that data, the same source or single truth source of data right off the bat. So there's less just engineering rework. So you're definitely seeing that. But then when you get into what would traditionally be more expensive cost drivers in your development phase, right, which is a lot of your flight testing, V&V testing, you're able to do a lot more of that by high fidelity models being able to use for analysis or verification by analysis. So that's a big one. And then of course in when you get later on in production, you would expect even more savings in production efficiencies, as well as again ONS. So that's a great question. It'd probably take a while to answer that efficiently and appropriately, but and unfortunately I can't share any numbers today.
Okay, I think we have time for this one last one, and then I'll turn it back over to Karen to close this out. What MBSE architecture, I'm sorry, that one I think I covered. What digital systems are becoming the leading edge standards, for example, Innovia or Cameo, etc.? That one's from Brian.
That's a great question too. I mean, that's definitely, so we have a model-based engineering roadmap and also an MBSE roadmap, right, that is doing just that, is trying to lay out what are the future processes and tools that we will evolve into that are more efficient, more effective for the engineering teams to use, as well as other functions. So, today we're using Cameo, No Magic that is part of more of the Dassault suite of tools, but on the BDS side, or the defense side, we're integrating those tools with other more traditional IPDM and Team Center, Siemens, PLM tools on our commercial side. Those tools we are utilizing the Dassault suite of tools right out of the box with your CATIA, Delmia, Process Simulate, and those such tools, as well as MDAO and other things. So Model Center, I mean, there's a whole bunch of tools out there that we're working to integrate.
I think that'll do it for the questions. Karen, do you want to say anything before we go?
Sure, I'll just add one last thing to that question. So what we've found over the years is that oftentimes there are movements to try to down select to one particular tool, and that's the one that's everyone's going to use within the company. And then we find that that never works. So like Brian was saying, there are a variety of tools. The question specifically asked about Inovia and CATIA. So like for CAD tools, I know we use different ones at Boeing. The same thing for like the cost analysis, or the same thing for the like model-based systems engineering. So I think it will depend upon a couple of things. What the function is, what or who your customer is, and what they want. So I don't think there'll ever be like one set of tools that everybody's going to be using. There'll always be some, a couple of tools here and there that'll do the same things. But going back to closing out this meeting, we hope you enjoyed the discussion. If you have more questions for Brian or for anyone from the OEM COG, just reach out to us, or you could reach out to Megan, or the ICEA organization. And then if you have any interest in participating in the OEM COG, again, let us know. And if you have a particular topic you would like us to address, let us know. Some of the previous topics we talked about were affordability, and then we also just gave some general comments about how ICEA could support the value of ICEA for the OEMs, and how that differs from, say, the DoD or some of the tool providers. So again, thank you for joining us, and we'll talk to you next time.